All right, guys. Today we are on page 13 of our trig graphing note packet. We started, I think, depending how much time we had last class, tangent and cotangent. Today we're going to graph secant and cosecant. So what I would like you to do on this page, you can actually do both of these things right now. I would like you to draw a graph of y equals sine x on the top graph on your paper, and I would like you to graph y equals cosine x at the bottom of your page. Don't worry about the secant or cosecant now. I just want you to really carefully graph sine x and really carefully graph cosine x, keeping in mind all of those quadrantal values. So be as accurate as you can. You don't need to plot the pi over 6s and pi over 4s and pi over 3s, but graph as accurately as you can from negative 2 pi to positive 2 pi. And then when you're done, you can unpause the video. So pause while you're doing that. When you're done, you can unpause and we'll talk about cosecant and secant. So go ahead and do that now, please. All right, so hopefully you paused and got that done. Here is my nice, neat, organized graph of y equals sine x. So we know that sine and cosecant are reciprocals. They're not inverses. We've been careful with that word. They are reciprocals of each other. All right, so cosecant x is the same thing as 1 over sine x. So there's a really important note, I guess, from that piece of information. If the sine of x is equal to 0, this function becomes 1 over 0, and it makes cosecant undefined. So first, really important note, I'm going to put some little stars, I think. Yeah. I'm going to put little stars wherever the sine function is equal to 0. Okay? Where that function is equal to 0, it makes cosecant undefined. And when a function is undefined, we've spent time on this earlier in the year, we know there's either a whole or an asymptote there. So in this case, since nothing divides out, every spot where the sine parent function is equal to 0, the cosecant function is going to be undefined. So that's the first kind of important guideline when we're doing this. So these vertical asymptotes occur basically starting at 0, so starting at the first place where sine is 0, and then occurring every pi, so 1 pi, 1 pi, every 1 pi left and right of that. All right, so this is the parent function. Obviously, if there's transformations, if there's changes to the period, that will all change, but the period of the cosecant function is also 2 pi. Okay, and then the frequency will change that once we start dealing with transformations, but the period is 2 pi. So the other thing that we're going to be able to use to our advantage, using our knowledge of reciprocal functions, we know when sine is 0, this output becomes 1 over 0. If the sine is 1, so wherever the sine value is 1, the output becomes, for the reciprocal, 1 over 1, which is just equal to 1. So we know that on the cosecant function, whenever the sine is 1, cosecant is going to be 1. Whenever sine is negative 1, cosecant is going to be negative 1. And we can kind of keep doing this for all the points, but you can see the shape that's starting to take place. This blue graph here is the cosecant function. It's the reciprocal of sine. All right, and I'm going to do my best. I'm on my laptop, so it's a little harder. Notice I'm not making it like this. It's not a square bottom. It's not like an absolute value like this. It's a smooth periodic curve, just like the sine function. And then it turns upwards and hits those vertical asymptotes. Same thing here. And right what you see in front of you, just those two graphs, is one period of the cosecant function. Here's another period starting at 0 and ending at 2 pi. And this will keep repeating itself over and over and over again. So what you see there is the graph of cosecant x. In next class, we're going to be doing all the same transformations that we've been doing, just using these reciprocal functions. So 2 important notes: the maximum points of sine x correspond with the minimum points of cosecant and vice versa. And as I mentioned above, the x-intercepts of y equals sine x correspond with the asymptotes of the cosecant function. And the asymptotes happen starting at 0, because that's where sine is 0, and every interval of pi before and after that. So when you see notation like this, k basically represents any constant integer. So k is 1, 2, 3, 4, 5, any interval of pi plus or minus from our starting point. So there's cosecant. All right, let's move it on. Let's do secant. So the same thing's going to happen. So hopefully you graphed cosine x. If you didn't, please do it now. And I kind of went quickly through that before. I hope you guys were good with your sine graph. We should be good at this point. But here's my parent function of cosine. Cosine starts here. When the angle measure is 0, cosine is 1. At pi over 2, cosine is 0. At pi, cosine is -1. So that's how I got that graph. I just plotted our quadrantal values, traced that nice smooth curve. All right, so the same thing happens. I'm not going to write all this down again, but secant is the reciprocal of cosine, so the same thing happens. When cosine is 0, anywhere where the cosine is 0, secant becomes undefined. So there's where my vertical asymptotes will take place. Notice it's different from cosecant, obviously, but it's the same pattern. Starting at pi over 2, every pi before or after that is where our vertical asymptotes are. And then same rule applies for the maximum and minimums. When cosine is 1, secant is 1. When cosine is -1, secant's -1, and then so on and so forth. So you probably know where we're going with this. So we kind of get that one period cut off at this side of our graph. Obviously, if you want, you could extend it. But if we're just strictly graphing from -2 pi, we only have that half of a curve over there. But then we continue on. Each minimum corresponds with a maximum. Each maximum corresponds with a minimum. And then we turn upwards or downwards towards our vertical asymptotes. And there you have it. And that's where we finish off our period. So same thing, the period of a secant graph is 2 pi, because it takes 2 pi of distance, I guess, on the x-axis to repeat itself. And then same notes. All right, so we're going to use this knowledge, there's the bell, to do some graphing of these functions next class. All right, so at the top of the next page, one last thing. We're still going to be looking at our BHAK. We'll talk about some very important things to look out for when you're doing especially these vertical shifts. So the K value, as far as those vertical asymptotes go, we need to be very careful about that. Think about our order of operations. So the B and the H have to happen first, and that's going to affect our vertical asymptotes. But everything else is the same. The A value affects the vertical stretch and shrink, and therefore the maximum and minimum points. But there's not really an amplitude. An amplitude kind of refers to the stretch from a midline. So it's like the stretch above and below that midline that we talked about. Secant and cosecant don't really have amplitudes because there's not a true height, but it does affect that vertical stretch or shrink. When the frequency is different, So when that frequency is not 1, we can still use 2 pi over b to find our period. So that hasn't changed. And then the h isn't a phase shift, so it's not a phase shift because this graph isn't really cyclical. It does repeat itself, but it doesn't kind of pick up and leave off kind of over and over again in this same matter. So just kind of picky vocabulary there. We just think of this as a horizontal translation and not a phase shift. And that's it. So I don't know what my timing was. I feel like that was a short video, but I always say that, and then I look back and it's like 14 minutes. But we're going to pick up next class. We're going to do a bunch of graphing of these reciprocal functions, and then we'll go from there. So let me know if you have any questions. I will talk to you guys next time. Let's see, 10 minutes. All right, world record. All right, I'll see you guys. Bye.